Hi, I'm Dr. Tom Calabrese, and welcome to this edition of Insights into Computer Science. This week, we'll turn our attention to how computer science is used in real life. To this point, we've studied the algorithmic approach to problem solving, programming basics, advanced data structures, hardware primitives, and some interesting classic algorithms. If you've been watching this series, you are well aware of the power of algorithmic analysis, memory manipulation for constructing real-world things through the use of data structures, and design alternatives for improving efficiencies and effectiveness. I personally find that very interesting and fun to do. This week, I want to take you into some of the application domains, the areas of real-world problem solving where we might put our computer science skills to good use. There are many application domains out there to look at, including financial software analysis, accounting software, data science, statistical and trend analysis, entertainment, music, art, real-time domains that would include things like process control, manufacturing systems, weapons systems, detection, electronic countermeasures, and so many others. Think about your car, for example. When you're driving, you're being controlled by so many systems that are monitoring the efficiencies of your vehicle, things like what your tire pressures are, the performance of your engine, how you're driving, are you drifting out of your lane, and then helping to encourage you to take corrective actions by flashing lights on the dashboard or bumping your seat a little to get you awake if it thinks you're asleep. Software is in every part of our life, and so there are tons of software domains that you should be thinking about. It is really hard to think of things we do in our daily lives that don't include automation, computers, and some level of software logic. It is important that while you are learning the techniques of computer scientists, you should also be understanding and building background in the application domains where you envision yourself applying your craft. I started my career as an engineer designing and building networking products like multiplexers, bridges, modems, and routers. This is an application domain that falls under the heading of real-time systems. I created software that followed the rules of network protocols while fielding packets moving through the network or the internet on a real-time basis. Developing software for network systems is very interesting and requires a considerable amount of familiarization with network engineering topics. It turns out that developing software for these systems uses a concept known as the finite state machine design, or FSM for short. What that means is that in a network system, there are a finite set of states that can govern where the machine, the network machine, is in the processing of packets. There are also a finite number of real-time events that can happen. And as a result, when we match the events in the states, we come up with the actions that take care of the result of every state-event pairing. Sounds complicated, but really it isn't. Rather, it is just a new way of looking at the problem-solving process. A really simple example of this would be to consider the finite state machine associated with, say, a soda machine. As you can see, a simple soda machine can be in only one of several states at a time. It can be waiting or refrigerating, basically doing nothing, idling. It can be counting money. It can be selecting a soda. It can be dispensing a soda, or it can be making change so that we can move on to the next transaction. Notice that each of the states ends in an ing, indicating an action to be accomplished while in that state. Now, we also have a finite number of events. You can insert a coin. The count of the money can exceed the price of the soda. You can push one of the selection buttons or pull a return lever. The machine can drop a can when the count equals the price, or it can drop a can if the count of money exceeds the price. The machine can also drop change. Now, if we put these into a diagram known as the finite state diagram, we see that the system is a closed loop, meaning there's no dead ends. There's no islands of computing. Everything is connected, and there's a loop that you can use to move through the system back to the waiting state. Now, this is important because in a finite state machine design, there can't be any places where the machine has to make decisions that aren't accounted for by the event and the state parents. In this case, we have 5 states and 7 events, or 35 event state parents. Now, interestingly, the diagram shows only the perfect or preferred path of machine operation. So picture that you go in and you put in a coin, and then you put another coin, and eventually you add up to the total of the soda, and then you press the selection button, and then the soda drops out of the machine, and then it goes back to waiting for the next person to start entering coins. However, if we look at all of the 35 pairings in what is known as a transition matrix, we can see that it is really pretty easy to take a comprehensive look at how the machine works under all possible conditions. So what happens, for example, if you're in the counting state and someone pushes a select button? Well, obviously you have to ignore it because they haven't paid enough money yet, which is different than what happens when they are in the selecting state and take the same action. Here, you move to the dispensing state where you give them their soda and, if necessary, their change. So, what does all this have to do with a networking device? Well, if you think about it, a networking device is a computer, and it has protocols that run in software. The router in this example operates in the same manner. It has states in the software, events in the software, and it takes actions. For example, the data forwarding algorithm looks at an incoming packet and determines if the address in the destination field is for a local machine in that network. If it is, it would move to examine the local ARP cache for local addresses to deliver the message to, say, via Ethernet. If not, it would look inside the routing table of the router for a remote router to forward the message to so that it could continue to make progress towards its final destination. Now, this style of problem solving and programming is very different from that which we might find in an application domain like finance, or more specifically market analysis. Here in the finance application domain, we have many events and no real defined boundaries for the problem. Instead, the financial analyst is looking for trends in the market data. So, for example, reviewing stock performance as a function of other market variables. In this case, a computer scientist would realize that it is not the problem-solving method, as we saw just previously, that requires attention, but rather the creation of a language that encompasses the flexibility to extract data in accordance with various patterns, perform an array of statistical tests, connect to data sources that we haven't even considered at the time the language was created, such as Google or Yahoo Finance or whatever, and we have to be able to create effective reports through which the analyst can work with the data and apply their knowledge. So really, the language supports the knowledge of the analyst. This is more of an expert system, or dare we say, an AI system. These systems require that the computer scientist creates software that does the primitive analysis. It, quote unquote, understands the extraction parameters of the data and can create or customize the reports and user feedback in accordance with the problem specifications. Turns out a language like R meets many of these needs. R was constructed to be a visualization language that has deep support for statistical analysis type things. This means that besides all of the statistical prowess of the language, its real strength lies in its ability to create powerful graphics and visualizations of the data that it's working on. These visualizations are very robust, yet only require a handful of instructions that can be applied by less experienced software designers. This is exactly what is needed in the financial analysis application domain. We want the financial analyst to be concerned with finance, not programming. As you can see from the examples provided, the R programming language is easily applied to at-large data sets, say in Yahoo Financial, to obtain interesting trend-based graphics. My favorite application domain is cryptography and information security. Cryptography has a rich history that is closely connected with the evolution of computers and sophisticated algorithmic thinking. Literally translated, cryptography means hidden writing. Evidence of manual cryptographic manipulations date back to early biblical times. Around 500 BC, the Spartan army used a cryptographic device known as a skytail to generate ciphers. Essentially, the skytail is a ribbon wrapped around a dowel of a particular diameter. The message is written across the ribbon horizontally. When the ribbon is wound around the dowel of the same size, the message is easily seen. But when you unwind the ribbon, the message is garbled as letters are now out of order. Rewrap the ribbon and the message is back again as long as the dowel is the same size. This is known as a monoalphabetic or one alphabet transposition cipher. Another early cipher was the Caesar shift cipher. In this cipher, you map the letters in your message to the corresponding letter in a shifted alphabet. For example, the letter A is represented in the cipher as a D. B is represented as an E, C is represented as an F, and so on. For example, the word boy in a 3-shift Caesar cipher is enciphered as E for B, R for O, and B for Y. Notice that the Y is shifted 3 by saying Z, then wrapping around A, B. Using a wrap in the alphabet makes this possible. Shifts like this are known as monoalphabetic, again, one alphabet, substitution ciphers. There are many other monoalphabetic substitution and transposition ciphers that serve the encryption needs of armies and emperors for thousands of years. Eventually, these monoalphabetic ciphers became vulnerable to attack. During the Renaissance period, mathematicians were the rock stars of the period. They started to consider the use of statistical analysis and probability theories to decode these ciphers based on the analysis of real language. In today's language, say English, it's not hard to see how 2-letter or 3-letter English words can be resolved by only a handful of real words. It is also common to see certain letter groupings go together, like TH or RE. QU is an exceptionally well-connected grouping of letters. This type of analysis makes the monoalphabetic cipher weak and rendered them basically useless for any practical purposes. Now, don't get me wrong, they're still popular at parties and to use for fun, but today with modern computing, these methods would be cracked almost instantaneously. In response to these analyses, the cryptographers of the Renaissance period created many polyalphabetic ciphers, such as the Vigneri square. The square requires the use of a cryptographic key. You go to the grid and map the letter of the key to the corresponding place of that key in the message, the plain text, and the intersecting square is the cipher code. To decipher the message, simply do it backwards to reveal the plain text or the original message. So let's take, for example, a key, AXYZBT. On the message, the quick brown fox jumps over the lazy dog, which, if you were from old school typing class, you would know that that uses every letter in the English alphabet at least one time. You would then match each letter to a letter in the key, and then when the key expired, you would put the key under the next grouping of letters in the message, and then put the key into the next grouping of letters in the message, and so on until you finish the message. In this particular case, the quick brown fox jumps over the lazy dog would translate into TEC PVB CHZ QPP CNMWK and MMQMWXRQ GDMTZVCNH. Notice the power of the polyalphabetic cipher in that there are no statistical anomalies to exploit in the cipher code. The letter M, for example, in the cipher is used 5 times, representing the O, the M, the P, the O, and the L in the original message. In other words, you cannot use the plain text corresponding to any M in the cipher to predict what the next M in the cipher will represent. In 1790, Thomas Jefferson created a cipher tool known as the Jefferson Wheel cipher. This was also a polyalphabetic cipher. The technology was considered so advanced at the time that he hid his creation for fear that an enemy to the US might get hold of it and use it against us. It is an incredible device that allows the user to set the polyalphabetic key that changes each of the 36 wheels to any of the 26 letters of the alphabet, thus creating 36 to the 26th possible configurations of the wheel. Now, this is a really big number. Go plug it into your calculator. Just prior to World War II, the inventor Arthur Scherbius created a mechanical polyalphabetic cipher machine known as Enigma. Enigma was an electromechanical device that originally had a keyboard, a patch panel, 3 encryption disks, a reversing drum, and a light panel that was used with a keyword of the day to create what were thought to be uncrackable ciphers. If you get a chance, you should look at the movie The Imitation Game, which talks about Alan Turing and all of the work that went on to break the Enigma codes. Of course, at this time, this was being used to merely encode design secrets for cars. As the war got closer, the Nazis took control of this device and used it to create ciphers to control the Wolfpack submarines in the North Atlantic. These subs were extremely disruptive and were effective in destroying supply ships and troop transports bound for England. At the same time, the Japanese were creating cipher machines of their own. Purple and JN25 were 2 of the most effective. In the US, the famous cryptanalysts William and Elizabeth Freeman were busy cracking codes and creating mathematical theories such as Friedman's index of coincidence test that could be used to determine if a cipher was polyalphabetic or monoalphabetic. Friedman proved that there was obscure connections between mathematics and what was then considered the art of cryptography that could be used to exploit the codes. Friedman and his team later cracked the purple code that was based on telephone relays and allowed US government officials to eavesdrop on diplomatic ciphers that were being sent from Japan to their diplomats in Washington. By the second year of the war, German cryptographers began modifying the design of Enigma to add additional wheels, making the device impervious to guessing and manual attacks that were known at the time. In the United Kingdom, at a secret facility known as Bletchley Park, a group of young and ambitious code breakers were tasked with breaking the Enigma code. Among them, as we just said, was Alan Turing. Turing had been, for years, experimenting with what he called thinking machines, early computers. Turing was convinced that the only way to defeat Enigma was to create a machine that could outthink the Enigma machine. He created the Bomba machine. The machine eventually proved to be the answer, and the Allies were able to crack the Enigma code, and this changed the course of the war in the Atlantic. Based on his work, Alan Turing became known as the father of the modern computer. Other famous cryptanalysts of the time included Lieutenant Commander Joseph Rochefort, who cracked the JN25 code just prior to the Battle of Midway. Marian Rejewski, who was able to recreate the original simplified Enigma machine and bring it out of Poland just prior to the invasion in the war. And of course, the well-known cryptanalyst who at the time was just starting out, Claude Shannon, who, as we'll see, transforms the thinking about cryptography and its vulnerabilities in our current set of cryptographic software. Shortly after the war, the US government commissioned Shannon to evaluate cryptographic methods and to create an opinion as to the direction that modern cryptography should take. Shannon responded with two famous papers. The first, A Mathematical Theory of Cryptography in 1945, and then Communication Theory of Secrecy Systems in 1949. In these papers, Shannon discussed the predictability of the current, at the time, ciphers, and espoused a new approach to creating ciphers in the future. He presented a framework of 5 principles that would make ciphers unbreakable. The first of these principles was that ciphers should be bit-oriented rather than character-oriented. Now think about this for a second. A character is represented in a computer as 8 bits. So just by making something bit-oriented, we've increased the complexity of our system 8-fold. Up till this time, all ciphers were character-oriented. Each character was replaced by some other character, whether it was polyalphabetic or monoalphabetic. It was a simple substitution at that point. During the end of the Renaissance period, a cryptographer known as Sir Francis Bacon created this concept of the Bacon bilateral cipher, which is a 5-bit character, not the 8-bit that we use today. And he was able to take those bits and manipulate them inside the letters of the cryptographic message to be conveyed. He would also hide those bits in his writing. So at the time, typical end of mail messages would end with a biblical passage. And if you look at those early examples, if he slanted a letter to the left, it would be considered a 0. If he slanted a letter to the right, it would be considered a 1. If you knew what to look for, you would be able to come up with your codes of 1s and 0s. This is known as steganography, the ability to hide a message basically in plain sight. And Sir Francis Bacon created what I think is Bacon bits. But at the time, he was so far ahead of his peers that they saw no reason to go through all this trouble. Claude Shannon thought otherwise. The second of these principles is that ciphers need to use confusion. This means that the cryptographic method must be hard to follow. The algorithm must be difficult to understand and thus hard to reverse. Now, what I think is interesting about this is confusion can be caused by many different things. Like, for example, adding in random numbers or using decimal numbers that don't repeat themselves, like the golden ratio or pi. Sometimes you see those things, and as a cryptanalyst, you have no idea why they're there, and you start to follow a chain of reasoning that turns out to have absolutely no real meaning, but causes this idea of confusion. The third principle is to use diffusion. Now, that's interesting because it means you want to change or optimize the bit changes between the plain text and the ciphertext. Now, this will prevent predictability. So, for example, if I create a key that reverses all the bits from 0 to 1 or 1 to 0, that would be pretty easy to figure out after a while. But if I only change, say, 48 to 61% of the bits, that would make things really tough for the cryptanalyst to figure out. Ciphers should use keys. Now, remember, monoalphabetic ciphers don't use keys, and polyalphabetic ciphers use keys. And what Shannon considered was the longer the key, the stronger the key. So you want to be able to make fairly complex keys that would make the discovery of that key very unlikely. Today, we use keys that are greater than 128 bits. Some are as big as 2,000 bits and beyond. Ciphers should use what is known as hard math. That means the math is easy to do, but hard to undo. So for example, most people think multiplication is easy, but division, they say, well, that's hard. Exponentiation is easy, but its reverse logarithms are hard, etc. Shannon's principles were embraced by the industry at large, and all of today's modern ciphers are based on them. So, as you can see, the application domain that you are most interested in will deeply affect your approach to computer science learning. In the next couple of installments of Insights into Computer Science, I'll go into more detail about the creation of cryptographic software because I feel that that particular application domain not only gives us something to think about, but in today's world, cipher and cryptography and cybersecurity are among the hottest topics in our industry. We'll cover symmetrical cryptography as defined by Horst Feistel and take a look at TIA, tiny encryption algorithm, which is an implementation that corresponds to the Feistel design, and we'll be able to understand those principles in action. We'll look further at hash algorithms and how they are emerging as the key ingredient in blockchains. We'll look at asymmetrical algorithms, and then finally, we'll take a look at Bitcoin and the application that we now know is revolutionizing how we think of banking and currency. So until next time,